Okay, so in today's example, we're going to look at how do we use the limit definition of a derivative to find the derivative. We're going to start out with a fairly simple polynomial example, and in later examples, we'll look at non-polynomial functions. So let's suppose that we have the function f of x equals x squared minus 3x minus 4. So just a simple quadratic. Now, before we get into the nuts and bolts of this, recall that we've already discovered that when we have a quadratic function, we're pretty confident that the rate of change of a quadratic function is linear. So our expectation at this point is that what comes out of this work is that we will wind up with a derivative function that is a linear function. All right? So let's remind ourselves the definition using the limit of a derivative. So we've defined the derivative of f, we call it f prime, to be equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Now, before we go further, I just want to remind you that what we've figured out is that really this is just the slope. So if we look at this numerator here, that's basically just y2 minus y1. And the denominator is basically x2 minus x1. Excuse me. So all we're doing is finding slope, right? But we're allowing the distance between the two x coordinates to get increasingly smaller. And in fact, by using the limit, we're letting it get infinitely small. Okay, so as we mentioned in class, that the limit is sort of like this, magical mathematical tool that allows us to really find the slope at one point, even though slope requires 2 points. All right, so the example that we have is x squared minus 3x minus 4. So we're going to have the limit as h goes to 0 of, now I've got to plug in x plus h into this function. So that means I'm going to have x plus h squared minus 3 times x plus h minus 4 minus, and this is important here, important enough that I'm going to change colors here to just show you that when we subtract the function itself, we need to put it in parentheses. So notice, oops, I wrote that incorrectly. Let me erase that. So notice we're going to write minus, and now we're going to subtract the entire function itself. So x squared minus 3x minus 4. And I see a lot of times students, that's where they make a mistake, is they forget to put this in parentheses so they don't subtract the entire function there. All divided by h. Now, at this point, let's just make a comment that we've got an issue here, because this function, this y2 minus y1 over x2 minus x1, is not defined at h equals 0. So I can't plug in h equals 0 at this point. And this is where your algebra skills are going to come into play. So what we have to do is we have to simplify what's here, and hopefully what we can do is somehow at least evaluate this limit as h approaches 0 by hopefully being able to plug in h. Now, remember, if that's the case, it has to be a continuous function. Okay, so here's what we're going to do. So this is equal to the limit as h goes to 0. So now I've got to simplify this using algebra. Now, if you don't recall, I would suggest you just go off to the side and say, I'm just going to multiply this by itself and use FOIL. But what you wind up with is x squared plus 2xh plus h squared minus 3x minus 3h minus 4. So all I did was square this out right here. So this right here, I just squared it out, and then I just distributed this right there, okay? So that's all that happened there. minus, now notice I'm going to multiply the negative through this second parentheses here, so I'm going to have minus x squared plus 3x plus 4. And this is all over h. Now, if we've done things right, at least with a polynomial, then what we will find is that a lot of stuff cancels out. And notice, sure enough, the x squareds cancel out. The negative 3x cancels here with the positive 3x, and the minus 4 cancels out with the positive 4. And so what I'm left with here is I'm left with these three terms in the numerator. And what's unique about them all is that they all have an h in them. So what I can do is I can say, okay, this will equal the limit as h goes to 0. So what I'm going to do is I'm going to factor out an h in the numerator. So I'm going to have 2x plus h minus 3 all over h. And this is where the important step really comes in, because now these h's will cancel out right here. And so I will have that cancels with that. And so what I wind up with is the limit as h goes to 0 of 2x plus h minus 3. Now, this function is continuous at h equals 0, so I can just plug h equals 0 in, and when I do that, I get 2x minus 3, and we're claiming that this is the derivative function. Now, important to note what we said earlier. Sure enough, the derivative function of this quadratic is a linear function, okay? And so that's something that we want to pay attention to. Now, what we have on this next screen here, actually I guess this screen, is we have a graph of the original function here. So this is the graph of f of x, all right? And what I'm going to graph in blue is a graph of the derivative. Now, if we look at this, this is 2x minus 3. So we have a y-intercept of negative 3, which is going to be about right here. And we're going to go up 2 and over 1. But I think another way to think through this, if you think about this, where does this equal 0? So if I set that equal to 0, so if I say, where does f prime of x, which is 2x minus 3, where does it equal 0? Well, I get 2x equals 3, so x equals 3 halves. So at 1.5, I know it's 0, so I can come here to 1.5, and then basically I have this function here is, I'll tell you what, let me redo that. So I can cheat on this note-taking app and have it draw a really nice line through these. Okay, so there is my derivative function, and so this is f prime of x, okay? And let's just verify that it makes sense graphically that this is the derivative. First off, note that starting right here, if I think about dividing this graph up into two different pieces, to the left of this value here, the function is decreasing the entire time, right? And to the right of this value, the function is increasing. Now, we've already stated that when a function is decreasing, its derivative should be negative. And you will note that right here, in this section right here, going this way, the derivative is always negative. And notice, moreover, that if you think about the steepness of the derivative, so let me do some tangent lines here. If we think about the steepness of the derivative here, you will note that it's always getting less and less steep, i.e., it's getting closer and closer to a very flat or shallow or horizontal line. And right here, the derivative, the slope of the tangent line is 0. So this makes sense that the derivative is more negative here, then it hits 0, and then all these tangent lines are positive. Okay, and from here over, the derivative is positive, okay? Okay, so real quickly go back. We had to use the limit definition, which remind ourselves is just slopes, and we're just taking the limit as h goes to 0. And then we do a lot of algebra here, and that's why, we always are saying, how big a deal algebra is in calculus. But we wind up with, and this is important, we wind up with a derivative function that is linear, which coincides with what we discovered earlier about the way that quadratic functions, they change over time, okay? And so our derivative function is 2x minus 3, and that makes sense graphically. All right, so let's have you try one. So what I'm going to do here is I'm going to give you an example, and I want you to pause the video, and I want you to try to work it out, and then I'm going to show you how it works. Okay, so let's see here. Let's go with the function f of x equals 2x squared minus 5x plus 1. All right. Now, once again, this is quadratic. For the moment, we'll stay there. And so we expect the answer to be some sort of linear function. All right, so pause the video. Try to come up with the derivative using the limit definition. That's really important. For any of you who have already had calculus, you're going to have to be able to do this using the limit definition. So make sure you use the limit definition and then see if you can verify graphically that it makes sense. Okay? Okay, hopefully you were able to get that done. Let's look at it here. So as we've mentioned, the derivative is the limit as h goes to 0 of, I'm going to plug x plus h in here. And remember, at this point, we want to make sure that we use parentheses here, or a bracket if you want, and then we're going to put in the function. And that's important because otherwise it's really easy to forget to multiply it all by a negative. Okay, all over h. Okay, so that equals the limit as h goes to 0. And so I'm going to multiply this out. Now, I get x squared, but it's multiplied by 2, so I'm going to have 2x squared. And then I get 2xh multiplied by 2 is 4xh. And then I get h squared, so plus 2h squared. Minus 5x minus 5h plus 1 minus 2x squared plus 5x plus 2. No, minus 1, sorry. Minus 1. Okay. All over h. Okay, so now let's kind of just go through and make sure we see what all cancels. The 2x squareds cancel, the 5x's cancel, and the 1's cancel. And notice what I'm left with, everything has an h. So that's really actually pretty important here in this example. So I get the limit as h goes to 0 of, so I'm going to have a 4xh plus 2h squared minus 5h all over h. Now, before I go any further, I want to make a note here or say something to everybody, because I find that students want to just do the sort of the algebra work and not carry on the limit. But it's really important from a mathematical standpoint that we realize we started taking the limit here. So if I think about this here, and I haven't taken the limit yet, so I still have to write the limit as h goes to 0 every time, because until the last step, really, I don't take the limit. So I'm going to have the limit of, and I'm going to factor out this h, and I get 4x plus 2h minus 5 all over h. And then once again, these guys cancel. And so then I'm left with the limit as h goes to 0 of, let's see, that's going to be 4x plus 2h minus 5. Now I'm going to take the limit by plugging in h equals 0, and the reason I can do this is this function here. So the one that I'm underlining here, this function is now continuous at h equals 0, and so I can plug in h equals 0, and what I wind up with is 4x minus 5. And note, once again, that this is a linear function, and that's what we expect when we have a quadratic. Now, just to kind of make really good sense to us from a graphical standpoint, if I were to graph this function here, so let me graph this. So it's 2x squared minus 5x plus 1. So we know we have a y-intercept of 1. I'm going to say that this is 1 here. And it's opening up. And so it's probably going to be the case that I have, you know, something like this. Okay. Something-ish like that. Okay. And now we said the derivative is 4x minus 5. So that is a linear function. So I'm going to do it in red. So that would be a linear function. And notice that this will equal 0. So this, if I set this equal to 0, I get x equals 5/4 or 1.25. So we know that what's happening here is this is crossing right here. And so if I do this, this function would look like this, right? And we would have that as our, now that for some reason it moved it over, but at any rate, it crosses right there at 1.25. Okay, so this is how we can use the limit definition of the derivative to find a derivative.